Last time, we talked about an immature Type 3 civilization under the civilizational range model. If you haven't seen the previous videos on this topic, do check them out. The link is in the description below. Today, we will be exploring a mature Type 3 civilization and some of its defining characteristics. According to Zubrin, a major challenge that humans will face as we become a Type 2 and then Type 3 civilization is that of transforming the environments found on other planets to more Earth-like conditions. This must be done because environments friendly to life are a product of the activity of life. In other words, when we begin exploring other stellar systems in our galaxy as an immature Type 3, it is unlikely that we will find worlds that meet our needs. So we will simply have to transform the environments of these worlds according to our liking if we are to advance to the next stage in our civilizational evolution. This process of planetary engineering on different worlds is referred to as terraforming. So how would we even begin such a monumental task? Well, Zubrin suggests a few possible ideas for different worlds. As we travel further and further into our galaxy, we are bound to find many Mars-like worlds. Since Mars will be the first extraterrestrial world that will be terraformed, the engineering methods by which this can be done are relatively well understood. The first step will be to set up factories to produce artificial greenhouse gases, such as perfluoromethane, and release them into the atmosphere. If we could release 1,000 tons of these greenhouse gases per hour, similar to how we release chlorofluorocarbon on Earth, then we could potentially increase the average temperature of Mars-like worlds to about 10 degrees Celsius within a few decades. This temperature rise would cause carbon dioxide gas to be released from the rocky material of the surface, further adding to global climate change. As a result, the amount of water vapor will also exponentially increase in the atmosphere, warming the planet further. At this point, we would be able to release methanogenic and ammonia-creating bacteria into the now livable environment, which will cause a further warming effect since methane and ammonia are very strong greenhouse gases. So the net result of such a program could be the creation of a Mars with acceptable atmospheric pressure and temperature, and liquid water on its surface within 50 years of the start of the program. Now, although humans will still not be able to breathe on the surface without breathing gear, there would be several advantages of living on a partially terraformed Mars-like planet. With these conditions, we would no longer need spacesuits to work outside. Our crops would grow in the open and large supplies of water would be much more accessible than ever before. Moreover, aquatic life would flourish in lakes and ponds oxygenated by algae, and city-sized habitation domes would be constructed as there would be no pressure difference between their interior and the outside world. But these are just the short-term advantages. We can certainly do better. In the long term, we could spread our most efficient plants across the surface of these partially terraformed Mars-like worlds to release oxygen into their atmospheres so humans can breathe without the need of any special gear. This process by itself may take up to 1,000 years. However, an advanced mature Type 3 civilization will have future biotechnology that could allow the creation of more efficient plants, or they may have other technologies available that could accelerate the oxygenation of Mars-like worlds considerably. One thing to note here is that on our journey to the stars, we may encounter young Mars-like worlds in their warm, wet youth. If this is the case, then terraforming would become much easier. For example, we would be able to skip the large-scale industrial process of releasing greenhouse gases into the atmosphere and move directly to the step of releasing and spreading bacteria and plants to further warm and oxygenate the planet. Thus, a team of interstellar explorers who chance upon a young Mars could initiate massive terraforming operations with little more equipment than an appropriate array of bacterial cultures, seeds, and a bioengineering lab. Now, Mars-like worlds are just one type among others. What if we come across worlds that are too hot like our very own planet Venus? How will future humanity or any other mature Type 3 civilization in the universe deal with this? Well, there are a few proposals for this as well. Venus was once thought of as a world rich with steaming jungles beneath its thick atmosphere, since it is very similar to Earth in terms of its size, distance from the Sun, and gravity. But of course, we know today that Venus is nothing like our home. Its surface temperature is so hot that it can even melt lead. But this is not because the planet is a little closer to the Sun than the Earth. Venus's clouds are so reflective that it absorbs even less sunlight than the Earth. Based on the amount of sunlight it absorbs, Venus should be colder than Canada. Instead, it is as hot as a self-cleaning oven. So what is going on then? It turns out that the real culprit is not the intense sunlight, but the internal greenhouse effect caused by the thick CO2 atmosphere. So if the CO2 atmosphere of Venus is what is causing the planet to burn, getting rid of it would be the ideal choice. This is exactly what Carl Sagan proposed in 1961. Sagan thought that Venus could be terraformed using aerial algae. He argued that Venus could be cooled by dispersing photosynthetic organisms in its atmosphere that could convert it from greenhousing CO2 to transparent and breathable oxygen. However, there are a few major problems with this approach according to Zubrin. First, while algae have been found in rainwater, there are no plants that actually live in an aerial habitat. And second, perhaps the biggest problem of this proposal is that Venus does not have enough water to support photosynthesis, even if we can somehow engineer plants and algae to survive in aerial habitats. So for Zubrin, the only other way to cool Venus would be to block out the Sun with a huge solar sail about twice the diameter of Venus. Although it would be a very large project requiring millions of tons of material extracted from asteroids, it would be well within the capabilities of an advanced Type 2 civilization, let alone a mature Type 3. Such a sail could be stationed at the position between Venus and the Sun, blocking over 90% of the Sun rays, leading to the precipitation of Venus's CO2 atmosphere as dry ice after a cooling off period of about 200 years. The dry ice can then be buried, and by moving the sail around in a small orbit, an acceptable surface temperature and day-night cycle on Venus-like worlds can be created. Even if we achieve this, Venus-like planets would still be very dry and may require an outside water source. However, encountering young Venus-like planets would be far more beneficial in comparison. Although the temperatures would still be very hot, the conditions on these worlds would be able to support large oceans just like the Earth. So terraforming young Venus-like worlds would only require a large solar sail and would be a well worthwhile project, since the result would be an Earth-sized planet complete with temperate oceans and a moderate pressure nitrogen-dominated atmosphere, fully ready for a rapid propagation of life. Now, while Sagan's idea of terraforming Venus would not work on Venus-like worlds, it would work on another class of planets known as young Earths. The Earth had a thick CO2 atmosphere in its early days, but because our Sun was also weaker at the time, the Earth did not turn into a Venus-like environment. However, there may be young Earths out there that are baking like Venus. In such cases, appropriately selected or bioengineered photosynthetic organisms might be able to rapidly terraform the planet to fully Earth-like conditions without any additional macro-engineering effort. So Carl Sagan did in fact have the right idea, but it was just applied to the wrong world. But what about worlds that are frozen like Titan, the moon of Saturn, or Callisto, the moon of Jupiter? How do we deal with these kinds of worlds? Well, the answer is still large solar sails. Using solar sails as reflectors to increase solar flux will be a useful auxiliary technique in melting the permafrost and activating the hydrospheres of cold Mars-like, Titan-like, and Callisto-like worlds. So using solar sail mirrors, an advanced civilization would be able to change the environment of these cold worlds to Earth-like temperatures, melt surface water ice into oceans, and vaporize dry ice to create a CO2 atmosphere. Thus, the ability to manufacture large, thin solar sails in space, a central skill for engineering of both Type 2 interplanetary transportation and emergent Type 3 Starship propulsion, is also a key technology for terraforming Mars-like, Titan-like, Callisto-like, and young Venus moist greenhouse worlds. Now so far, we have looked at the class of planets that are free to rotate about their own axes while orbiting their parent star. But the majority of planets in our galaxy will most likely be tidally locked to their parent star due to factors such as the distance and size of both the star and the planet. Meaning, it would orbit the star with the same face always pointed to the star, just like the moon always points the same side towards Earth. This is a problem because only one side receiving warmth and illumination from its star can become inhospitably hot if the planet is close enough. Or if it is far enough, the dark side could become so cold that it freezes out the entire atmosphere of the planet. To deal with this problem, Zubrin proposes to use orbiting sunshades or mirrors. In the case of a tidally locked planet with a permanently lit too hot sunward pointing surface, we can just put a sunshade in orbit about the planet with a period equal to the desired day. This sunshade would only need to be as big as the planet and relatively closer as well, unlike the Venus sunshade. In the case of the tidally locked planet whose sunlit side is temperate but whose dark side is too cold, we need to position a mirror levitated by sunlight pressure so that it could always be used to project light onto the cold hemisphere of the planet. If done correctly, we should be able to generate enough gas in the atmosphere so that substantial atmospheric convection will even out most of the temperature differences between the sunlit and night side hemispheres. An alternative to this method would be to impart rotation to the tidally locked planet. A mature Type 3 civilization should be able to get the tidally locked worlds rotating by bombarding them with multiple asteroid hits. For example, if the target planet is only the size of the moon, a 116-day rotation could be induced with a single 100-kilometer asteroid hit, which means a 12-day light-dark cycle could be created with 10 such hits. But if the planet is Mars-sized, the magnitude and effort would increase by a factor of 17, whereas an Earth-sized planet would need almost 300 times as many such impacts to do the same job. Now this method is something that humanity can only handle when it reaches a certain maturity as a civilization, meaning we must reach the status of a mature Type 3 in order to tackle projects of this magnitude. Apart from this, a mature Type 3 civilization will have robotics, bioengineering, nanotechnology, as well as picotechnology available to them. This is because terraforming planets will require a significant amount of work and people who attempt it will need helpers. So robotics will play a crucial role in terraforming and all other extraterrestrial engineering projects. But human-scale robots may not be as efficient, so an advanced civilization would be able to create self-replicating, microscopic, programmable automatons or nanobots out of the artificial structures built to design specifications on the molecular level. The reason for this is that parts for large robots need to be manufactured in advance, whereas the molecules used as parts for nanobots either come ready-made or can be readily assembled from atoms. So while building a nanorobot would undoubtedly be more difficult than constructing a normal-sized robot, nanobots are the only kind that hold the promise of being potentially self-replicated in a true sense of the word. The basic idea is that once we learn how to manipulate individual atoms and molecules, machines can be constructed using small clumps of atoms as gears, rods, wheels, and so on. Now to build macroscopic structures, billions of nanorobots would have to group themselves together to form large robots, perhaps on the human scale or even much bigger. They would then turn their attention to accomplishing some tasks they had been programmed to execute, such as inspecting a human body for cancer cells and to make appropriate adjustments, manufacture huge solar sails from asteroids, or terraform a planet. This may sound too good to be true, but there is nothing in the known laws of physics that forbids the existence of self-replicating nanotechnology. In fact, mathematician John von Neumann proved that self-replicating automatons are possible way back in the 1940s. So humanity too can one day have this technology under its belt. But that's not all. When humanity advances further as a mature Type 3 civilization, it would be able to build machines not out of atoms or molecules, but from subatomic particles such as atomic nuclei, known as picotechnology, operating on a scale thousands of times smaller and faster than even nanomachines. Such technology might draw its energy not from chemical reactions, but from far faster, more powerful nuclear reactions. The capabilities of such pico machines could only be described today as sheer magic. Using these advanced methods of construction, a mature Type 3 civilization of this model would be able to create ring worlds as well as space colonies. It may also build Dyson spheres, but Zubrin believes that these megastructures are too impractical as they require an enormous amount of material. So it is unlikely that these civilizations would entertain this idea and instead focus on the much more practical ring worlds and space colonies. So using vast supplies of fusion energy, sophisticated space technology, and very advanced robotics, humans in the era of Type 3 civilization will hollow out asteroids and Oort cloud objects to create miniature enclosed worlds. But there still remains one more thing to discuss that will distinguish a mature Type 3 civilization from the rest: their ability to create stars. Without stars, life as we know it would be impossible. Stars are the sources of life since they help make heavier elements, without which the universe and life wouldn't be the same. But as we now know, there are numerous worlds too far from any star to support life. Moreover, most of the stars in our galaxy, such as red dwarfs, are much dimmer than our sun, and brown dwarfs are incapable of igniting fusion reactions due to their small sizes, which leaves planets orbiting them in endlessly frozen darkness. So how can a mature Type 3 deal with this situation? Well, it would simply light their fires. If an advanced civilization comes across a red dwarf, it could amplify its power by using solar sails to reflect back a small portion of the star's output. The rate at which thermonuclear fusion proceeds in a star goes as a strong power of its temperature. For proton-to-proton fusion in a star the size and temperature of our Sun, reaction rate scales as the fourth power of the temperature, whereas for cooler stars the temperature dependence is stronger. So even increasing the temperature of a star by a small amount through reheating with reflected light can cause a large increase in generated power. This increased output will cause the star's temperature to rise further, which will amplify the output yet again. But what if the star in question is a brown dwarf or a gas giant incapable of sustained fusion reaction? Well, in that case, Type 3 astro-engineers will have to use black holes to get the reaction going. If an appropriately sized black hole were to be placed within a brown dwarf or any other massive Jupiter-like object, it would start swallowing mass, but in the process produce a huge output of radiation that would push back against the infalling material. This would very quickly regulate the rate of infall to a steady state known as the Eddington limit, creating a fully functional star. Although these artificial stars may only last about 10 million years, a fraction of the time of our Sun, the inhabitants of the planet around them will be advanced Type 3 people, equipped with a full grab bag of terraforming anti-greenhouse techniques. They should be able to handle the situation without any difficulty. So an advanced Type 3 civilization wouldn't just be capable of bringing planets to life, but also entire stellar systems as well. In his book, The Star Maker, written in the 1930s, British philosopher Olaf Stapledon wrote, "Gods will never be, but star making is a very noble profession." So it is clear for Zubrin then that stars have made life. Life should therefore make stars. But as advanced as a mature Type 3 civilization may sound, according to Zubrin, it will still never be able to expand to mastery of the entire galactic theater. The distances involved are too great, and the required time for the activity is too long. So for him, a Type 3 civilization could at most expand a region of about 50 light years in their respective galaxies. He believes that there may be plenty of advanced civilizations out there in any given galaxy, and that even a Type 3 civilization has a finite lifespan of about 25 to 50,000 years. Based on his calculations of the Drake equation, there should be plenty of Type 3 civilizations out there. So for Zubrin, these advanced Type 3s could also wipe each other out for resources. Or a simple bad idea spreading like a virus, similar to how memes spread in today's world, could do the trick. Regardless, a galactic civilization will not be an empire spread from a single Type 3, but a society of many Type 3 civilizations linked together. This is what makes a Type 3 of the civilizational range scale qualitatively different from the other types. Now, in order for humanity to join the Galactic Club, we must at least reach the maturity of a Type 3 civilization. If we don't, then encountering a Type 3 civilization will be psychologically devastating for humanity according to Zubrin. We cannot survive with the thought that we are beings of a lesser order. Turning off the radio telescopes to perform a kind of cosmic withdrawal is not an option, as it amounts to conceding inferiority in advance. The only solution is to grow up, regardless of whether there are others out there in the galaxy. We must do it for our own sakes. Type 3 calls. And that brings us to the end of this video. If you stuck around this far, do leave a like, share, and subscribe to our channel if you want to see more content like this. We really do appreciate your support. Will humanity ever reach a mature Type 3 status under the civilizational range model? Also, what do you think a Type 4 civilization would be capable of under this scale? We will look at this in detail at a later time, but for now, would love to hear your thoughts in the comment section down below. Until then, we'll see you in the next one.